So let's start this section with a seemingly very sort of obvious question: why don't you fall through the floor? So you're standing on the floor, think, well, why the hell don't you fall through that? And somebody who doesn't do physics might say something like, well, the floor is solid, and that's what stops you falling through it. Well, if you think about at the smallest possible scale that we've looked at so far, so what is inside an atom, if you remember Rutherford's experiments firing radiation at really thinly beaten out gold foil, Rutherford found that atoms are mostly empty space. So when you stand on the floor, you are standing really on empty space. So why the hell, if all solid objects are mostly empty space, because all solid objects are made from atoms and atoms are mostly empty space, why the hell don't you see through stuff? And that's also the same sort of question as why don't you fall through the floor? Well, although an atom is mostly empty space, what is whizzing around the outside of an atom? Well, electrons are whizzing around the outside of an atom, and it's those electrons which mean you can't see through solid stuff, and it's those electrons which mean you don't fall through the floor. So what's going on? Here are the electrons in your foot. Here are the electrons on the floor. We've not shown the atoms which each electron is associated with. We've just shown the outer electrons. Now you can see in red, each electron has an electric force field, and it's these electric force fields which repel from each other, which means you never actually touch anything solid. What you feel when you stand on the ground is actually the repulsion between these electric force fields. So electric force fields is what we kick off this section with. Okay, so why do the electrons never actually touch? Because the fields repel. So here are pictures of electrons, and if the electrons are far apart, you've got these beautiful radial force fields. If you bring electrons close together, then the force fields repel. Now if you're thinking this looks very much like two magnets, if you bring two north ends of a magnet together or two south ends of a magnet together and they repel, then yeah, well done. It is the same picture as magnets, as the magnetic fields. Why? Because electric forces and magnetic forces and electric fields and magnetic fields both come ultimately from the same fundamental force, which is called electromagnetism. And electromagnetism is where electric forces, electric fields, and magnetic forces and magnetic fields come from. So they're very, very similar. So what the hell even is a field? We see these pictures with field lines on. What the hell is a field? Well, think of a field as an area of influence. And in these areas of influences, particles with a particular characteristic feel a force. So in the case of a gravity field, it's particles with mass which feel a force. In the case of an electric force field, it's particles with charge which feel a force. In a magnetic force field, it's particles made of iron which feel a force. So what the hell are these things, field lines? Field lines show you the direction which something with the characteristic, with the required characteristic, would feel a force on. It's the direction that a particle would feel a force on if you were to bring that particle close to it. And if you want to see these field lines, then what we do is we sprinkle on some tiny particles which are going to be affected. And these particles tend to line up. They're so small that they don't either rush in towards the middle, or they don't, in this case, immediately get pushed out. They're so small they kind of line up. That's what the forces do. They sort of line up. They're not big enough to be kind of moved around as a whole. They line up, and it kind of shows us very clearly what direction a bigger particle would move in if we put it there. So if we put, like, I don't know, an electron there, electron would repel, and it would feel a force going out the way in the direction of the force field lines, in the field lines. Okay. So electrical fields are why you never actually touch anything, why molecules attract and repel and do chemistry. So all of chemistry is about sharing and swapping electrons, and sharing and swapping electrons is governed by these electric force fields. Electric force fields are how you put a force on something. So if you, I don't know, hit a wall, you are not actually, your atoms are not actually touching the wall. The outer electrons in your fist are almost meeting the outer electrons in the wall, but the repulsion between the two is Newton's third law, equal and opposite forces. Electric force fields are why solid things feel solid. It's why you don't fall through the floor. Electric force fields govern our everyday interactions, really. Pretty much everything we do, apart from being kept from floating off, which is gravity, pretty much everything we do is explained by electric force fields. So electric force fields only seem mysterious when you make them from micro scale, which is what we've been discussing, up to macro scale. So you make the force fields bigger and bigger, usefully big, so we can do stuff. So here we have, these are called parallel plates, and we make one parallel plate really, really positively electrically charged and one very, very negatively electrically charged, and we have an electric force field between the two. Now if we then put a charged particle in that force field, then we can make those, then that force field will make the charged particle move. So opposites attract, so if we put an electron there, the little electric force field around the electron, which we've seen in blue, interacts with the external electric force field, which is in red, and there's a force of attraction and the little electron accelerates. So we can calculate stuff. We can calculate how much energy that electric force field gives to the charged particle. So energy, physical energy from the field, is often given the really old-fashioned word for energy, which is work. So energy equals work, and the energy which the charged particle is given depends on the particle's charge, Q, and the voltage of the electric field. This kind of, if you rearrange this formula, you will hopefully see that V is W over Q, which explains to you what voltage actually means. We've always talked about voltage being like the push down the electron pipe, or the electrical pressure, but voltage is actually the energy given to each coulomb of charge. So if you've got a 1.5 volt battery, that means each little coulomb of charge gets given 1.5 joules of energy, 1.5 joules per coulomb of charge. Now, once you have worked out the energy which a given charged particle is going to be given, it's usually a proton or an electron, then you can work out the speed with which this charged particle is going to be moving at because of this energy. Now this energy is going to be kinetic energy, so you're going to use the formula Ek equals half mv squared, Ek being the same as EW, which is what you've worked out. M, the mass of the particle, can be found on the data sheet. It's going to be something like a proton or an electron. So we've looked at electric fields. So electric fields tend to accelerate a charged particle. Now magnetic fields tend to change the direction of a charged particle. So magnetic fields, anything involving moving electric charge, will experience a force if that is going through a magnetic field. Now moving electric charges can come in various forms. They can be a wire carrying electrons. So this is how motors work actually. A motor will have like an external magnetic field, and there'll be wires sort of wrapped around a spindle in the middle of the motor, and the wires, which are obviously carrying electrons, the electrical wires, experience a force, and this makes the spindle sort of spin. So electrical wires carrying electrons certainly experience a force if that wire is put inside a magnetic field, but also sort of solo moving particles, so like a solo electron or a solo proton, because these carry charge, if these solo particles go through a magnetic field, they experience a force as well. So magnetic fields tend to change the direction of travel of moving charged particles. Electric fields accelerate, and magnetic fields tend to change the direction. So you can work out the direction that the force is going to be acting on a charged particle when the charged particle goes into a magnetic field. And the first thing you've got to ask yourself, is the charged particle positively charged or is it negatively charged? If it's negatively charged, then you use your right hand to do the stuff we're going to describe. If it's Did I say positive? If it's negatively charged, you're going to use the right hand. If it's positively charged, you're going to use the left hand. Okay. I remember this with the phrase Royal Navy. Right hand is for negative particles. You remember it however you want to remember it. Okay. So the first finger is pointing in the direction of the magnetic field. So magnetic fields go from north to south. So the magnetic field will be pointing towards the south, so point in that direction with your first finger. The middle finger is the charged particle's original direction, and once you've placed your first finger and your middle finger, then the thumb will be giving you the direction which the force acts on the charged particle. Right, what's the point in learning about electric force fields accelerating and magnetic force fields changing direction? Well, it's because this is how particle accelerators work. So the first type of particle accelerator which was invented didn't even actually bother with the complication of magnetic force fields to change direction. It just stuck charged particles in a really super duper intense electric field, and it accelerated them, and at the negative end, well, in this case it's the negative end because the proton is accelerating towards the negative end, there was a target, and we slammed the proton into the target, and we saw what happened. This is still actually how X-rays are produced. Now the linear particle accelerators are sort of huge. They're like half a mile long, but you can get really small ones, and the really small ones are how X-rays are made. Because when the proton slams into the target, it decelerates really quickly. It gives out energy in the form of photons of light, which are X-rays. So linear accelerators are fine, but because they just go through the linear tube once, there's a limit to how much energy they can pick up from the electric field. So then cyclotrons were invented. Now cyclotrons are used in hospitals, and the charged particle, usually a proton, pops out in the middle, and in between the two Ds there's the electric field, and it accelerates the charged particle. So the charged particle in the middle accelerates towards this D. Now there's a magnetic field in this D, and it swings it round, then it accelerates across the gap again, then it swung around again, then it accelerates across the gap again, it swung around again, accelerates across the gap, and it swung around again. As it gets faster and faster and faster, the particle can't corner as tightly. So the swinging around takes up a greater and greater distance, and at some point the charged particle, usually a proton, shoots out the side. This is a cyclotron. Imagine looking down from above. Now the good thing about cyclotrons is that they are compact. Hospitals use cyclotrons to create protons, beams of protons, for proton beam therapy for cancer. But because they're so compact, there is a limit to the kinetic energy they can give to the particle. And it's because as they get faster and faster and faster, they can't corner as tightly, and so there becomes a limit. So if we want to keep on giving these charged particles more and more and more and more and more energy, then we have to use things called synchrotrons. So linear accelerator, straight line, one run through from the start to the end, so the kinetic energy is limited. Cyclotrons, they're compact, but there's still a limit to the amount of kinetic energy because the charged particle has to be able to corner. Synchrotrons have, now these are enormous. The sort of circumference of these synchrotrons are like, well, the big ones in CERN is like something like 20 to 30 miles all the way around, and so we have an electric field, and then all the way around we have electromagnets to keep them sort of cornering, and every time they go through the electric field they accelerate, so they speed up and they speed up and they speed up. Now